nullator with an infinite input and infinite impedance, because there you don't see anything here. But I might as well make this thing with current controlled current sources, and then the input impedance will be 0. And basically, from the nuller, we know that the input voltage of the nullator equals 0 and the current equals 0. So the ratio current divided by voltage, voltage divided by current, sorry, is undefined. 0 divided by 0. It can be any value. So the input impedance of the nuller is not infinite, it's not 0, but I will show you that you can also, with making an input impedance of 0, make a nuller. And that's what I will show you here on this paper. If I go to my paper, so here's my paper. And let's design it ourselves. Let's make a current controlled current source of which the current will flow, will be the current from the narrator. So let's say here, and I have a current gain of unity. So here in some short, I have a gain of unity. This current is copied in this. Then I sum the two, which gives me 0 current at this point, because this is equal to this, and you see it flows like this, nothing left here. And this is my output of the narrator. So here, I can place another current controlled current source, having any gain, because the current here equals 0. So it means that this current will be 0 and the voltage will be 0. And now I have a short instead of an open circuit at the input. And in order to show you that this is really true, I prepared a simulation. And in the simulation, you see here, this is what we discussed before. This is the symbol in symmetrics for a voltage controlled voltage source. So this is the input, the gain of unity, and the output voltage. And here between those two nodes, the voltage will be 0, because this voltage equals this voltage. And here I put the output of another voltage controlled voltage source, of which the input then is the nullator. So I have a voltage of 1 gain here, 1 volt here, input source impedance 1K, and you see I connected to the input, so there will be, let's say this is a voltage feedback amplifier. This is 10K and 1 ohm, so the amplification is 10,001, and you see exactly 10.001K here. So it's a perfect number, this one. Now let's do the other one with the current controlled current source. And you see here is the current controlled current source. Input and output current are subtracted, so the resulting current in this node will be 0. And this only is there to isolate the input from the output, but it can have any gain, and the current in this wire will be 0 in all cases. And you see exactly if I put 1 volt here, 1K here, there's no voltage drop across here, so there's no current flowing. There's 1 volt here and 1 volt there, and 10,001 volts at the output. So both are good implementations of nullers. And you see, I can also place here an impedance in parallel with the signal path. I can place here an impedance in series with the signal path. It doesn't matter, because voltage and current at the input are 0, and the input impedance of the nuller is undefined. Was this a clear demonstration? Otherwise, I need to improve. I see no comments on the chat. So I hope it is clear. Then I can go back to Chris. Stop share. Hello, Chris.
Hi. And here we go to the next question. The noise of a two-port must be modeled with noise sources. Well, most of you did that okay. And basically, it's a matter of the definition, the theory that says, which chapter in the book was that, Anton?
Sorry?
That the noise model?
of a two-port, that is in a network theory, no, in a noise in chapter 19.
Yeah. Well, then here we have a phantom zero in the loop gain of a negative feed amplifier will not appear in the gain. Well, also this is a good thing, a good answer, a good question, I think. And there is a video in that talks about it. I think if it's not, it's there today. I don't know where it is in the schedule at the moment. And then this one. This was a question that apparently was a complex one. So maybe, Anton, you should also explain something about this one. Swapping the input terminals or the output terminals of the controller in a feedback amplifier changes the sign of the transfer. And that's not true.
No, basically, you know, we designed the ideal gain of a feedback amplifier by using a nuller as controller. And the nuller nullifies, and there's not whatever a positive or a negative input. You can see if let's go to my screen again. Share screen. This one. So if I would change the gain here to -1, then I swap the input terminals and the result is the same. It doesn't change the 10K. You see, so the gain is not at all important. The sign of the input is not important because we are nullifying the difference. A 0 is 0. So the only thing we want to be sure of that if we implement the controller with a thing that has a finite gain, that the loop gain is negative, because then we can speak of corrective feedback, and an error will be corrected such that it converges to a stable output. That is what the sign of how you define the sign of your controller if it is not a nuller. But if you change it, it doesn't do anything. Let's say because you see here with a nuller in, you can change the sign here, but it's not important at all. So the sign of the controller, the only is the sign of the loop gain, and that is all. You can also do it like this. If you go to the formulas about the loop gain, then I switch to my paper again. You remember we had something like the gain with feedback equaled the asymptotic gain times minus loop gain divided by 1 minus loop gain. Well, let the loop gain go to infinity. So if I do the loop gain go to infinity or be, let's say, much larger in absolute value than 1, then it's just minus L over L over minus L, which means this goes to unity or a little bit different, but it doesn't swap a sign. Not at all. So now maybe you think because the amplifier is unstable that something happens with the sign of the thing, but let's do it. Let's just make an example of a voltage amplifier. And do positive feedback. Well, if this error signal is very, very small, so if there is a very large loop gain, so error is almost 0, then you could say that the voltage, if this is the voltage Vs, and so there's no current flowing and there is no voltage, so it acts like a nuller basically. The voltage Vs is there, it is also there. The current is Vs over, let's call this R1. So the current is also flowing there, Vs over R1. And you see that V here, let's call it V out, equals Vs times R1 plus R2 divided by R1. And it doesn't change anything if I change the sign. But this is not stable, which means that if you would build this in practice and you would apply a voltage, then the output will clip, because let's say a positive output voltage here generates a positive error signal here, generates again more positive voltage, so it will clip to the output. But if you would be able, and if the amplifier would be working in a linear region, and you would measure the small signal gain on the way that it would be clipping, it would just be this gain. And that's what we are talking about. We are talking about the small signal gain of the amplifier. So you can swap the terminals of the controller. The only thing it does is it causes instability, but it doesn't change the small signal gain. I hope this is clear. There's another question on the chat. About number 3, Chris.
Number 3?
Yeah, there's here. Can you do question 3 too? If it does not appear in the gain, why would you add the phantom zero? Well, that was everything that had to do with the phantom zero. We said that the gain of a feedback amplifier could be written as, if you select the reference variable properly, the ideal gain times minus L divided by 1 minus L. All can be a function of the Laplace variable, which means there are poles and zeros in the loop gain, and there can be poles and zeros in the ideal gain as well. Now, what will a phantom zero do? A phantom zero is defined as a zero in the loop gain that also appears as a pole in the ideal gain, basically in the asymptotic gain, but if they are equal, you can say also in the ideal gain, which means I put something like a, sorry for my telephone. I put, sorry again for my telephone. Okay, so let's say I can write the asymptotic, the thing as a, I put a pole in the asymptotic gain. So let's say that it will be the only pole. Then there will be 1 plus S tau here in the asymptotic gain. And I put a 0 in the loop gain, which will do here 1 minus LS, well, times this 0, which is 1 plus S tau. And here also 1 minus LS that I already have times 1 plus S tau. Now this one cancels with this one. And that is why you don't see the phantom zero in the gain. But it still changes the characteristic equation here. And that is the effect in which it corrects the high frequency response. So, and that was in the presentation of the phantom zero, and it will be on the web soon. Is this clear? It still influences the gain. Yes, of course, it influences the gain, but it does not appear as a 0 in the gain. And since we wanted to have an all-pole function, that is important. So it influences the gain, you're right. Otherwise, it would have no function at all. It's okay? Okay. Chris, it's up to you again.
Where were we? That one. By the way, if you look at this, this is what we as teachers see. You see here, for example, the bottom one, the discrimination index, that tells us something about how well this exercise discriminates between the better, say the high grade students and the low grade students. So in principle, this is a question we like as teachers because it separates, whereas when you have a low index, then the question doesn't do that very well. Here, well, this is no problem.
Like number 10 or so was a problem. Yes.
Yeah, 10. Yeah.
And it is very discriminating. So it is very good question from us. You see, 75%. It makes really distinguishing, separating good students from students who didn't understand. That's what we want with an exam. But still we can explain. But there was in a presentation of negative feedback that the controller only adds noise. So at best, the noise performance of a negative feedback amplifier can be as good as that of its controller. The noise sources of the feedback amplifier can be the same as those of the controller. And then we had non-inertic feedback. But usually the controller adds noise, so it can only become worse. So similar things could be said about the current and voltage drive capability. That also cannot be cured with negative feedback. Making large loop gain doesn't do anything with the voltage and current drive capability and doesn't do anything with the noise. So negative feedback can be considered as an error reduction technique, and the errors of interest can be midband accuracy, weak distortion, and bandwidth limitation. That's what negative feedback can improve.
And it can change your in and output impedance.
Of course, but let's say it's not errors.
Yeah. Well, that's it. Are there more questions about the test?
And this test is not representative for the exam, yes, because we didn't do, let's say, balanced questions about all difficulty levels, etc. This was just testing the process.
Could you explain question 9?
What is 9?
I'll look it up.
Okay, Jasper, shall I answer your question first? There's an example in the book of this voltage amplifier, and it is like on chapter negative feedback configurations, and then the noise.
I have question 9, Anton.
Oh, sorry. Yeah, but let me do the other one first. That is now open. Yeah. So in section 7.5.2, there are these noise transformations done for an example for a passive feedback voltage amplifier, and the starting point of your design is that you draw uncorrelated noise sources. Now, if you then split a current source or move a voltage source through a node, you get two correlated sources. And in the example, you see exactly how we deal with it, because then plus and minus signs become relevant because the two sources are correlated and they can even cancel. It is not that physically you are canceling noise. It's just during the modeling, you made a model and two things cancel. That's all. So then you add the coefficients so that you always end up with coefficients for your uncorrelated noise sources. And then you calculate the spectra from the spectra of these uncorrelated noise sources and the squared coefficients that you have. That is how you deal with plus and minus signs in your circuits. And that in my initial circuit in this example, voltage and current sources have arrows or plus and minus signs, only has to do with the fact that they are part of the symbol. In single loop negative feedback, input current comparison ideally results in zero input impedance. Yeah, but that is the design of negative feedback amplifier configurations and the principle of negative feedback in basically. So if we are at the input of the nullator subtracting two currents, and there will be no current flowing into your nullator, then all the current will flow into your feedback network and the voltage will be zero. So you have zero voltage and a finite current, which means zero input impedance. Just try to draw it yourself for a current amplifier. Let's say an amplifier like on shall I put it on the paper, Chris?
Yeah.
Share. Okay, so let's make a current amplifier with negative feedback and passive current, passive feedback. So we have a load. We want to sense the current. The load is grounded, so if I have my controller here I will sense the current in the opposite terminal. Make a current divider. Then a part of the current will be flowing here and subtract it from the source. So that is how I design a current amplifier. So here is the source, IS, and the source impedance CS, 1, 2. Now, if this controller is a nullor, then we have, this is the amplifier, an input current, which is not zero because that is the source current, you see. The voltage here is zero. So there's no current flowing in this impedance. All the current from the source will be flowing this way and this way. So we have a finite current called IS and zero voltage, which gives it zero input impedance. Something which is not zero, so that is zero, yes.